I'm Heike Wulff. I'm an associate professor in the Department of Pharmacology. So I'm typically teaching medical students, but my lab also does a lot of medicinal chemistry, so I'm part of the chemistry graduate group. And I'll be giving you 4 guest lectures on metabolism, toxicity, and formulation. And today I want to start with what is called ADME, absorption, distribution, metabolism, and elimination of drugs. 2 definitions before we start. A lot of people like to confuse these definitions. Pharmacodynamics are the actions of the drug on the body and the dose dependence of these actions. This means, what does the drug do? Does it bind to an enzyme? Does it bind to a receptor? And how potent is it? Pharmacokinetics is what we're talking about today. The actions of the body on the drug. How is your body or the body of an animal absorbing, distributing, metabolizing, and eliminating the drug? So again, try to not confuse these 2 terms. Pharmacodynamics is the mechanism of action. Pharmacokinetics is what does the body do with the drug. When we're talking about drugs, this is kind of our spectrum. You will hear that people use this term small molecule as opposed to peptides and proteins. You've already learned about Lipinski's rule of 5, and this is pretty much your range of small molecule drugs. Lithium, the world's smallest drug, used for manic depression. Morphine, this is really your typical small molecule drug. Easily absorbed, molecular weight around 300. And then as we're coming up in molecular weight to something like erythromycin, a macrolide antibiotic, you see the molecular weight is getting high. We're starting to violate Lipinski's rule of 5, and absorption is becoming difficult. And then as we really move up in molecular weight, we come to peptides and proteins. This is a cone snail toxin used for pain. This is insulin, molecular weight 6,000. Monoclonal antibody, molecular weight 150,000 Dalton. These molecules are way too large and way too polar to be absorbed. Peptides and proteins have to be injected. And of course, because they're peptides and proteins, if you would try to take them orally, this would be very expensive protein. So again, proteins and peptides are injected. Small molecules are typically taken orally. And that's why you hear a lot of people in medicinal chemistry use this term small molecule. And typically they mean something below 700 or 1,000 molecular weight. Okay, drugs can be administered in different ways. We can give them orally, and you'll find this abbreviation per-os or PO for it. Then we're going through the GI tract. Or we can give drugs by routes that bypass the GI tract. We can give them intravenously, IV, intramuscular, subcutaneously, rectal, through the nose. Drugs can be inhaled or applied on the skin. And when you're working in experimental animals, what you also very often do is IP, intraperitoneal. Animals that walk on 4 legs have a big IP space. I don't know if you have a dog or a cat, you can pick up the skin and there's a lot of space here. Primates and humans don't have much IP space, so you typically don't put drugs IP in people. Okay. From a conceptual model, intravenous is the easiest. It is, of course, technically a little difficult and carries a risk of infection. But when you're putting the drug directly into the vein, per definition, bioavailability is 100%. Because unless you miss the vein, there's no way how you can lose the drug. You're putting it all directly into circulation. You're all chemists, so I'm assuming you're familiar with modeling reaction kinetics or with modeling radioactive decay. So you probably all know what mono-exponential decay is. And that happens with a drug. If you put a drug into circulation by a bolus injection, you typically see a mono-exponential decay. I'm on a logarithmic y-axis here. This is the simplest model to describe the kinetics of a drug. Mono-exponential decay. But of course, life can be more complicated. Here we have a drug that is not just staying in circulation. Here we have a drug that is leaving circulation, that is partitioning between circulation and the tissue, like muscle. And then, when you model this, you get two slopes. One for distribution, one for elimination. This is bi-exponential decay. Here's a real-life example. This is an experimental drug we work with in the lab. My postdoc is injecting it into the tail vein of 3 rats. We're taking blood samples, and then we're using HPLC-MS to measure concentrations of this drug. And you see, on a linear scale, we're getting nice bi-exponential decay. We put this on a logarithmic scale, you see the two slopes. And you see this with a lot of drugs, that you have one quick distribution phase and then the real elimination. Okay, let's make it more complicated. Sometimes you have drugs that will do what the previous drug did, distribute between circulation and the tissue, but some drugs will then also go into a so-called deep compartment. And then you get tri-exponential decay. You get distribution, elimination, and slow redistribution out of this deep compartment. You're probably now wondering, what on earth are deep compartments? Deep compartments are bone or fat. These are tissues that are badly perfused, so drugs slowly accumulate in them and then are only slowly released out of these compartments. Famous example, DDT. This is an insecticide that is so lipophilic that it'll accumulate in the fat of mammals or any other animal and then accumulate up the food chain, because it just never comes out of the fat. The only time it ever comes out of the fat is when you starve. Or heavy metals are really famous for depositing in bone instead of calcium. So these are deep compartments. And depending on how lipophilic your drug is, you can actually have significant amounts of the drug in fat, which can slowly come out again. That's also famous for the cannabis metabolites. When you smoke cannabis, because cannabis goes, the tetrahydrocannabinoids go into fat, you can typically trace this afterwards for months, because the metabolites are still hanging out in the fat. Yes. And you know, the one thing about drug elimination, and we talk about this more, this real elimination phase is mono-exponential decay. And if you have, so you would really, theoretically, you would only reach 0 at infinity. So if you have a really sensitive analytical method, you can trace a drug for a long time. Okay, here's a real-life example of a drug in a 3-compartment model. We again give it IV, and on the linear slope, you know, you see it's hard to decide if this is second or third order. When you go on a logarithmic slope, you see that it fits better as a 3-compartment model. But this is something where at some point you really need to do experiments. Okay, this was IV, and what you've probably seen here in the plasma concentrations are these nice tight standard deviations between different animals. Let's now move on to oral. Here we're giving the same drug orally. And you see this now looks very different. We have 6 milligram, 50 milligram per kilo. We're getting an absorption phase. We're getting a sort of plateau where absorption and elimination are happening at the same time, and elimination. And the first thing you see here are these huge standard deviations between the different individuals. And I have to tell you here that oral application of drugs is the most variable route you can possibly do. You're typically getting up to 5-fold variations between different individuals. And the reason is because you're going through the GI tract. And I know you're not medical students, but I would like you to realize what going through the GI tract means. If we would pull out our GI tract, it would be 6 to 9 meters long. And our drug travels through this. You take it by mouth, it goes down the esophagus into the stomach, through the small intestines, and then large intestines, rectum, and anus. And as the drug follows this route, the pH varies. In the stomach, we're very acidic, 1 to 3. In the small intestines, it's slowly getting neutral until we're reaching slightly alkaline. And the thing to realize about the stomach is that it's really just a storage reservoir. Our stomach allows us to eat a large meal relatively quickly and then go on with whatever we're doing. The stomach will then pour acid on the food, basically sterilize it, and start to break it down. It's actually also a big muscle. So your stomach will crush the food, grind it up, mix it, liquefy it, and then when it's all nice and small, it'll press it through the pyloric canal into the small intestines. And I'm describing this here in so much detail because from an absorption standpoint, the stomach really sucks. You don't get much absorption in the stomach. It has a small surface area, it's acidic. So the only things that are absorbed out of the stomach are ethanol, because it's so membrane permeable, and weak acids, like aspirin or ibuprofen. Anything else is absorbed in the small intestines. And that's why the time it takes to go into the small intestines is so important. You probably remember from high school that in the small intestines you have these villi. If you would flatten those out, you get an impressive surface area, 250 square meters. That's a football field. That is a glorious surface for drug absorption. This is where your drugs are absorbed. And that's why the passage time out of the stomach matters so much. If you take a drug, or if you give it to an experimental animal on an empty stomach with a large glass of water, it'll be in the small intestines in no time. If you take your drug after eating 2 Big Macs, with a lot of fat and protein, it'll stay in the stomach for hours. And that's why you're getting these huge variations after oral administration, because passage time will vary between different individuals depending on what they've eaten and when and how. Okay, we've arrived in the small intestines, so let's now look at absorption. Drugs can be absorbed by active or passive processes. The active transport processes are really only important if your drug is a sugar, an amino acid, or a vitamin, or if it looks like a sugar, an amino acid, or a vitamin, and is taken up by these transporters. The majority of small molecule drugs are absorbed by diffusion. Simple diffusion through the lipid bilayer. And that's why it's so immensely important that your drug is membrane permeable. The number that everybody is always interested in is the famous bioavailability. This is a fraction of the drug that actually reaches the systemic circulation after an oral dose. And this is typically not 100%. It's typically somewhere in the range between 20 to 80 or 90%. And you determine it by giving the drug IV, measuring plasma concentrations, and getting the area under the curve. And then you give the same drug again, orally. You measure plasma concentrations. You ratio the areas under the curve, and you multiply by 100. And then you get your percent oral availability. And typically, to develop a drug orally, you want at least 40%. Okay, after your drug is absorbed, the first place it'll see is the liver. And if the liver is mean and metabolizes a significant amount of the drug, during this first liver passage, you call that first pass effect. And that is also bad to have for a drug. You know, you might have a drug that is 100% absorbed, but if the liver is metabolizing 80% of it on the first passage, it's not a very good drug. Okay, and this is a cartoon that might help you understand what is happening with the drug in the body. So far we've only talked about this process. We talked about absorption out of the intestines through the gut wall into the circulation. And we're going to talk today and on Friday about all the rest that is going to happen. But your drug basically needs to go through the gut wall. So it needs to pass through two membranes. It will reach the portal vein. It goes into the liver. It has to come out of the liver into circulation. And then in circulation, we have an equilibrium between plasma protein bound drug and free drug. And then eventually the drug might finally reach its target. So I'm also using this cartoon to give you an idea of how difficult is it actually to get the drug into the target organ. It has to go through a lot of barriers to finally reach its target. And of course, these are all steps that need to be investigated when you're really developing a drug. Because potency is really not everything. You might get a drug out of structure-activity work that is very, very potent, but if it's not absorbed, if it's metabolized very quickly, it's not a good drug. Okay. Some basic principles for distribution. Lipophilic drugs distribute readily throughout the body, but if they're too lipophilic, they get retained in fat. Hydrophilic drugs are retained in aqueous phases. Charged, highly polar drugs do not distribute readily, and that's sometimes not even absorbed. One of the big barriers in the body is the blood-brain barrier. In the brain, you have capillaries with very, very tight junctions between the cells. And it's incredibly difficult to get drugs through these tight junctions. Which means that basically all peptides, antibiotics, antibodies are excluded from the brain. Only small molecules with a molecular weight of less than 500 reach the brain. And ideally, you learn this later in Chem 130b, ideally you want to have a log P somewhere between 2 and 3, polar surface area less than 90 square angstrom, and a molecular weight around 300 to really get into the brain. Because this barrier is really good at excluding stuff. And to illustrate this, this is a radiogram of a monkey. And we're giving a 14C labeled neuroleptic drug. Very lipophilic molecule. And it's actually very effective at going into the CNS. So the whole brain here is white. This is the 14C from the promethazine. If you now put a quaternary group on the promethazine, it has become membrane impermeable. You see the CNS is now completely dark. This drug no longer goes into the brain. Not even a little bit. Okay. The other term you will find in literature, and that everybody is always interested in for a drug, because it's a very useful term, is the so-called volume of distribution. The volume of distribution is calculated by dividing the dose of the drug, which you know because you give it, by the concentration of the drug at time 0. Possible volume of distribution in the body are plasma, which is about 3 liters, blood, about 5 liters, extracellular fluid, so all the fluid surrounding your cells, about 20 liters, and total body water, about 40 to 60 liters. You determine this from the plasma decay, and because it's very difficult to measure drug concentration at time 0, because your drug hasn't really distributed, and it's also very difficult to already take blood while you're still giving the drug, what you typically do is that you extrapolate back from the decay to the y-axis, and then read your drug concentration at time 0 of the y-axis. You're so interested in this number because it tells you something about the drug. If you're developing a drug and you find from the PK that the volume of distribution is 3 liters, this tells you that the drug is bound to plasma proteins and staying in plasma. If you find a volume of distribution like this, 500 liters, that's not the analytical chemist making a mistake. This tells you this drug is not in plasma. This drug has left the circulation and it's all in tissue. And then if you want to know where the drug is, you would need to sacrifice the animal and analyze the tissues for the drug. But this volume of distribution gives you the first hint that this drug is going into tissue. Okay. In blood, drugs are bound to plasma proteins. The major plasma proteins are albumin, which is binding acidic drugs, and alpha-1 acidic glycoprotein, which is binding basic and lipophilic drugs. But in general, weak acids are typically highly plasma protein bound. Weak bases can be plasma protein bound, but they also really like to go into tissue. And for weak bases, you typically find these huge volumes of distribution. And of course, plasma protein binding is in equilibrium. Drugs will dissociate on and off albumin. Okay. Let's start looking at metabolism and elimination. Elimination is a combination of metabolism and excretion, whereby excretion is the real physical removal of the drug out of the body. Our major metabolizing organ is the liver, and the thing to realize about the liver is that its function is not to metabolize drugs. The function of the liver is to turn anything that we can't digest, anything that is not a carbohydrate, a protein, or a fat, into something that is more water soluble so that we can eliminate it. So we have enzymes in the liver that will metabolize alkaloids, terpenes, spices, stuff like curcumin. So anything that is lipophilic and that would accumulate in our body is being made more water soluble in the liver. And the liver happens to metabolize drugs, but its main purpose is to deal with anything lipophilic we eat. The liver is really perfect for metabolism. Blood flow is slow in the liver, and drugs can partition into the hepatocytes. And hepatocytes are metabolically extremely active cells. They do extensive protein synthesis on the rough ER, and then they have a smooth endoplasmic reticulum that is basically plastered with P450 enzymes. If you put liver into a blender, you get the famous liver microsomes, which are basically vesicles of smooth ER with P450 enzymes on them. And this is the whole point of drug metabolism. You take a lipophilic drug like phenytoin, it's hydroxylated by P450, and then it's conjugated to glucuronic acid or sulfate, and you've turned it from something very lipophilic into something that is very, very water soluble and easily excretable. And typically these drug metabolites are less active. We have one metabolic activity in plasma, which are esterases. So our plasma is very good at cleaving esters, like, for example, procaine. But then the serious metabolism happens in the liver. So the liver will take lipophilic drugs like benzene, functionalize them, oxidize them to a phenol. So the functionalization reactions are oxidation, reduction, and hydrolysis. When I teach medical students who hate chemistry, I typically tell them, okay, if you learn phase 1 reaction is stick a hydroxy group on it, you've described 90% of phase 1. And that is pretty much true. That's what P450 does. Stick hydroxy groups on molecules. And then you have a handle here for conjugation, to conjugate to sulfate or glucuronic acid. And again, you turned benzene into something that is much more water soluble. So what are these enzymes? This is a huge family of monooxidases. Some of them are so specific that they only turn over a single substrate. Other enzymes, like this one here, CYP3A4, are extremely promiscuous. This enzyme metabolizes 50 to 60% of all clinically used drugs. This is an impressive enzyme. These enzymes are called P450 because they hem proteins, and if you treat them with carbon monoxide, they form a pink complex that absorbs at 450 nanometers. So P simply means pink. Okay. This is what P450 does. It's actually two enzymes. The P450 enzyme itself and the flavine monooxygenase, which together perform a monooxygenation. They reductively cleave oxygen and transfer one oxygen atom onto the substrate. So you have the substrate, oxygen, NADPH, and a proton, and you get an alcohol, NADP+, and water. Okay, and in the interest of time, I know you're all waiting for your quiz. Look over this catalytic cycle at home. This is something that if we were doing bioinorganic chemistry, you could spend a whole quarter on just this catalytic cycle. But what you should remember is this. P450 enzymes are extremely versatile. They can oxidize anything you throw at them. They can oxidize tertiary carbons. Aromatic rings get epoxidized and then open to phenols. Carbon double, carbon triple bonds, carbon sulfur double bonds. Tertiary amines, secondary amines, amides, phosphines. Sulfur can be oxidized all the way, and then even silicium-containing compounds. The only bond in the world that P450 cannot break is the carbon fluoride bond, because that is too short and too strong. But otherwise, P450 can oxidize pretty much everything. And here's a few examples of this. You've already seen this. Oxidation of an aromatic ring to a phenol. Epoxidation here on a double bond in aldrine. And what P450 is also really good, and this is important, at doing is O and N dealkylation. So P450 likes to oxidize in alpha position to heteroatoms. So if you have methoxy groups on your drug molecule, P450 likes to take them off. So for example, codeine will be converted into morphine. You're oxidizing here and taking the CH3 group off. And then we do one step further. You see there's a CH3 group on the nitrogen here. P450 will then also take this group off, and we go from morphine to normorphine. So again, P450 is very good at taking alkyl groups off molecules. Okay. This is entertainment for you at home. Since I know you want to do your quiz, just read through this. Bottom line is, we do not know how CYP3A4 looks like. We have two contradictory crystal structures in the field. One which says that the active site is very small, and one which says that the active site is very flexible and can increase more than 80% in volume on substrate binding. So we still don't know how this amazing enzyme works. Okay, thank you.